All right, so now we're going to go ahead and we're going to take a look at spherical geometry with Gauss's law, but specifically for if the charge is not uniformly distributed in the sphere. So let's see what that looks like. So this will be case 4. So again, we're going to find E for charge distributed in a sphere of radius big R. Right now, I don't want the charge to be spread evenly. I'm going to instead describe how densely packed the charge is. I'm going to talk about my charge per volume. Okay, and that's a lot like the density you're used to from chemistry class, mass per volume, right? Grams per cubic centimeter or whatever. But now we're going to talk about it with charge, coulombs per cubic meter. Okay, and so we're going to call that the volumetric charge density. If we wanted to, we could talk about charge per surface area per square meter or something. That'd be my surface charge density. Or when we had a charge rod earlier with Coulomb's law, we used like our charge per length, right? Our linear charge density. We're going to do volumetric charge density for this problem. So we're going to say the charge distributed in a sphere of radius r with volumetric charge density Now, I want it to not be the same charge density everywhere. I want it to become more dense as I head to the surface, maybe. And so I want to say that the symbol I'm going to use for charge density is rho. Okay, and it looks a lot like, I drew that a little big, like a lowercase p that's kind of curly, right? Like a curly p that doesn't quite close on itself. We're going to say that that's rho as a function of r. Okay, and so maybe, for example, maybe my rho is, I don't know, 12r cubed or something. You know what I mean? Okay, it can be some function of r. Okay, so as r gets bigger, this gets more dense, right? More charge per. And again, my rho is going to be my charge per charge per cubic volume, right? So my charge per volume, or charge per coulombs per cubic meter. Okay. So there we go. So I want to find it. I'm going to start with for r greater than big R. Okay? In other words, outside the sphere. All right? So what does this look like? You say, well, look, I've got this sphere of charge spread out throughout it. Okay? And there's a sphere that has a radius big R. Okay, but I want to find the field strength somewhere way outside it. Maybe out here somewhere, out here, right? So maybe I want to find, I'm going to go ahead and draw it like this. That's little r, is that distance out there. Right there, let's find that field strength. Now, notice what I've told you here, or more importantly, what I haven't told you. I haven't told you what that total charge in the sphere is. Instead, I told you the radius of the sphere, and I told you the charge density function. So that'll make it actually, that's where the trick's going to come in. It's going to become a little trickier. So you say, well, if this is what my charge looks like, again, it makes sense that the electric field diagram, the electric field lines would just radiate outward from this positive charge. Again, if this was all negative, the field lines would go inward. But my field is going to radiate outward. And draw that real well, that's okay. You say, hey, what shape Gaussian surface am I going to want to draw for Gauss's law? And you say, well, I'm trying to find the E field here, so my surface needs to go there, and my surface needs to enclose charge. So I would like it so that that field will be at the same strength everywhere on the surface. So when I do my Gauss's law, integral over a closed surface of E dot dA equals the charge inside over epsilon naught. They say, I want to make this integral easy to solve, so I want to draw a surface where the E is constant everywhere on the surface, and that angle, that cosine theta there, look at the angle between E and A, it'd be swell if that cosine theta would be a constant value too. And then constants can factor out of the integral, and life is easy. So once again, we're going to do a sphere of radius little r. My bubble's going to surround the charge. My area vector always points straight outward. And you say, gosh, that's going to be nice and parallel to those field lines. If I had drawn the field lines long enough, then you would see what I mean. And so it's going to be cosine of 0 degrees again. And so this is going to be so nice. We say, okay, the E field is constant everywhere on that surface by symmetry. And so the E is a constant, it'll pop out everywhere on the surface, so it'll pop out of that integral. That cosine is going to be cosine of 0 degrees everywhere on that surface. That's going to be a constant, then I'll move out of the integral. All that's left is the integral of dA. In other words, I'm going to add up all the little bits of area. Well, if I add up all the little bits of area, that just gets me the surface area of the sphere. The surface area of the sphere is 4 pi r squared. And so you're like, Mr. C, we've seen this a ton. This is what we got for a point charge, or for a charge uniformly distributed. As long as I have radial symmetry, right? And I go to the right side, Qn, what's the charge inside? Well, it's just going to be the total charge over r squared, over epsilon naught. You say, that's what we got before. You say, oh, I don't know the total charge, though. You weren't given the total charge. Instead, I gave you the charge density. So it is the same setup as before. There's just one little hiccup, and that is I didn't tell you the total charge. So what we're going to do is we're going to quickly take a little detour. Let's find out what that total charge is, then we can stick it in there and solve. So here we go. New calculation. We're going to call this finding the total charge. I call that big Q. Okay. So how are we going to find the total charge in this guy? You say the charge is at a different density as I travel outward. The density is changing all the time. It's a function of r. So how do I do this? Well, what we're going to do is we're going to take that charge sphere and we're going to slice it up, slice into a bunch of infinitesimally little bits of charge, and then add them all up. By add, I mean integrate, right? So what we're going to do is we're going to say I'm going to take that total charge and I'm going to split it up into a whole bunch of little dq's, and I'm going to add them all up. All right, until I've added up all the dq's till I get the total q. That's how I get big Q. You say, okay, fine, that seems to make sense. You're like, okay, now how do I slice this into dq's? You're like, well, I don't want to go and do like vertical slices because like my rho is a function of distance from the center, and so my density would be different at different points on every slice, and that'd be nasty. I would like to make it so that the density is a set value for each slice. Each slice has the same value. So what shape do I want to make my slices? I want every point on that sliver, on that slice, a little bit of q, that dq, to be at the same r value. In other words, I'm going to slice it into spherical shells that are like nested inside each other. Concentric spherical shells. That's the solution. That's the technique that's going to work. So I'm going to take this guy and I'm going to slice it up. Watch, look. Into spherical shells until I've added up to the entire sphere. So if I look at so that's what I'm going to do. I'm going to look at just one of these shells. I didn't draw these really great, but that's okay. Look, I'm just going to draw another one. One of these little concentric spherical shells. There it is, right? Hey, that little guy right there, that contains a charge, dq. That little guy has some radius here, right? Okay, that's that. Okay. Okay. And so what I want to do is I want to add up all the little dq's for all the little bits here so I can find out what the total charge is of the sphere. The problem is that I don't know how much charge each little sliver has. But I do know the charge per volume because that's what this rho is. So what I'm going to end up doing is I'm going to end up changing my variable of integration here so I can do this integral so I can add up all these slivers. I don't know how to add up their charges directly, But what I do know is I know about this rho guy. So let's define rho now. All right, rho, my volumetric charge density, that's my charge per volume, right? Now, if I looked at just a little bit of charge, there'd be some ratio between that little bit of charge and the little bit of volume that that little spherical shell has. So this little dq also takes up a little d volume. Okay, and again, the shape that we're choosing here is called a spherical shell. Concentric spherical shells, they have the same center, nest on each other. So rearranging this, cover this up for a second. You say dq would be rho d bump. Okay, you see that's great. I could replace this integral in terms of charge with something in terms of volume. Except, again, my rho is in terms of r. So what I'm going to do is rewrite dvol in terms of r. In other words, there's a relationship between the radius of this shell and the volume of just this shell. Not the volume it takes up, the volume of the shell itself. So you're like, okay, how do I find the amount of space that that little shell takes up? And this is the tricky part. So what I'm going to do is I usually talk about the fact that when I was young, my family used to own a globe, okay? And this globe was like a cheap promotional material given out by National Geographic magazine for people that, my grandma liked to subscribe to National Geographic and gave us like the issues when she'd read them, and also gave us this globe. So the globe was like this cardboard sphere. But like they had printed the globe, the map of the Earth, on paper bits that they had then like pasted to the outside of the globe. Well, as we played around with it, you know, being kids and tossing the Earth around and stuff, as one does, that paper started to like kind of peel off. What did that look like? Well, let me take this one spherical shell out here. Now imagine this is the spherical shell, okay? So it's shaped like that, right? But if you were to take it and slice it, like along, remember it's a globe, so I slice it along a longitude line, one of those vertical lines, you know, north to south lines, you know that it would end up slice it, it would kind of look like that. You know what I mean? These lines of longitude, right, would end up looking like that. If you peel it off and laid it out flat, okay, you can do this probably like with an orange peel or something. It would be helpful if it was a really thin peel, though. It would look better with an apple or something, but we want a sphere. What this would look like when you slice it like that and lay it out flat, it would look like this. You may even have seen maps of the Earth shaped like this before, right? There's different ways of representing the Earth's surface. It's tricky to try to come up with something that's accurate because you're trying to show this 3D surface, right? This three-dimensional shape on a flat surface. And if you try to make it like a rectangular thing, you end up having to like stretch out the materials here. So like Greenland looks like it's huge, right? When it's really not that big, and so on, and Antarctica and so on. Things get magnified near the poles because of that. But anyway, if you took the paper and kind of laid it out, it would look like this. Now, this is that little dvol, right? Okay, this little thin layer, right, of this thin spherical shell, this thin shell. Now, the shell has some thickness to it. So imagine my little, if you want, orange peel, or for me, I always imagine, like I said, the paper on a globe. I agree, not everyone has had that experience of peeling the paper off a globe. And you should be proud of yourself that you have not done that to a globe. But anyway. All right, there we go, right? Yeah? Okay, now, the question now is, this little bit, this has a certain volume to it, right? This is a three-dimensional thing, right? Okay, and you say, how do you find the volume of this shape? See, well, the same way we do any shape. Like, look, see this? You know what that is? That's a little cylinder or a disc, a nice flat disc. It has a volume. Or this is a prism shape, right? Little triangular prism. Hey, that has a volume too. How do you calculate the volume of these shapes? What you're doing with these is you're saying, I'm going to take this 2D shape and I'm going to move it through the third dimension, sweep it through the third dimension. And so I'm going to take the area of that face and then sweep it through the third dimension, right? Through that thickness. Same thing with this. I'm going to take this little 2D shape, that area, and I'm going to sweep it through the third dimension, right? And that'll be the thickness. And you know what the volume is? It's the surface area times the thickness. The area of that top face times the thickness. So my volume, right, is surface area of the face times thickness. Maybe I should just say area times thickness, but I think you get the idea, right? So with this guy, I'm going to take that surface area, all the surface area here of that top surface, times the thickness. All right? Hey, what's the surface area of a sphere? You say, well, that outer surface, that's, again, formula AP formula sheet, that's 4 pi r squared. So d vol here for this guy, we're going to say, hey, that d vol, it's the surface area, 4 pi r squared, times the thickness. How thick do we want each of these infinitesimally small little spherical, nested spherical shells to be? How thick? It's a little d in the r-axis here, a little dr. That's the thickness, right, of that is going to be dr. Area is 4 pi r squared. And so the volume is 4 pi r squared dr. Surface area times thickness. That's the volume of one little sliver. So that is what's going to go in here for d vol. That seemed like a long walk for that answer, but here we go. So dq is going to be rho times 4 pi r squared dr. That's my dq. And what am I going to do with that dq? Well, that dq, I'm going to integrate that to find the total charge in this sphere of non-uniformly distributed charge. So my q is going to be my integral of rho 4 pi r squared dr. Now I've just changed the variable of integration, so I have to change my bounds so they correspond to the old bounds, but they're in terms of the new variable. Correspond to the old bounds, so they match with the old bounds, but they have to be in terms of that same new variable of integration. So I was going to add up, slice, 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 concentric shells, right? Adding up all those charge. Well, I'm going to go ahead and add from r equals, little r equals 0 to little r equals, and I'm going to add these shells until I get to the surface of that sphere of charge, which is at big R. So my bounds are going to be from little r equals 0 to little r equals big R. And that's the integral I'm going to do. Now, because rho is a function of r, rho is not going to move out of this integral. I have to stick that function of r, in this case, for example, 12r cubed, in there and then integrate. But this will give me my q. Okay, so I'll put that function in there. That'll give me my q. Once I have the total charge, that's what goes then, this answer then, goes in there. And I move my 4 pi r squared over and I get my E field strength. Should I go ahead and do this out for this example? From here on out, it's the physics is done. It's just the calculus. Do you want me to go ahead and put that 12r cubed in there for rho and then integrate this one? You can integrate a polynomial as well as I can, right? I mean, the 12 and the 4 and the pi would kick out of the integral, and so it would be the integral of r cubed times r squared. R to the 5th dr would be 1/6 r to the 6th, right? Times all that junk that I moved out. Anyway, that'll go in there. The r squared will come up down here. It'll cancel 2 of those r's. My E field will be proportional to r to the 4th power while I'm inside the sphere. Okay? Yep. Okay, good enough. That's what you do when you are outside the sphere and they don't tell you the total Q. Instead, they just tell you the volumetric charge density function. Okay, that was case 4. Now we're going to do case 5. Last case for insulators, spherical insulators. And you say, okay, great. What's case 5 going to be? Case 5 is the same setup, but what if we want to find the E field not outside that sphere of charge, but inside? Would you be offended if I jammed case 5 on the same board? No, I'm going to do it anyway. So here we go. I'm just going to give myself some space. I'm going to erase this. All right. I'm going to pull a line across. Case 5. Same as 4, but for R less than big R. In other words, inside, okay, that sphere of charge. We want to find the E field here now. So maybe there's some point up like here, right there. Whoop, there it is, right there. What's my E field strength there? How am I going to solve it? The same way we just solved this one. Like the same way. I'm still going to do my Gaussian surface. I just care, you say, I want to find the E field strength there. I'd like the E to be uniform, same strength everywhere on my surface, so it pops out of the integral. I'm going to do a sphere passing through this distance here. And this is my little r, right? I'm going to do my bubble. Going around there, yeah? Okay. Now, good news is, doing that shape, again, my little area vector always points straight outward, right? Out of my bubble. And my E is nice and parallel to that. So again, it's going to be cosine of 0 degrees. It's just going to be +1. It's going to be same everywhere on the sphere. It'll pop out. The E field's uniform because of the symmetry. Although I know I didn't draw this very symmetric, but I got a little off center there. But you get the idea. So the area, surface area of that bubble is 4 pi r squared. It's going to be the same left side again. The right side. We want to find the charge inside of this bubble now. We're trying to find the E field there. Just the charge that's inside matters. Remember in the last video, I said if I put a little charge outside the sphere, in the sphere, but this little charge here, the field this little guy makes that's outside the bubble, any field lines will radiate out from it. Any charge that goes into the bubble here will shoot out the other side, right? In the field that this guy makes. And so this guy, since flux going in is negative, flux going out is positive, the field line will just cancel itself out when we add up all the flux for this boundary. So it's only the charge inside that matters. So I can ignore this, all this charge out here, this like spherical shell, this thick spherical shell here outside, I can ignore. I just care about the charge that's inside my blue boundary here. That's all that matters. So I'm going to find the charge inside my Gaussian surface. How are we going to do it? We're going to split the charge inside my bubble into a bunch of concentric spherical shells, just like we did before to find the total charge. Everything's the same. Each shell's still going to be the little dq with a d volume, 4 pi r squared dr. Everything's the same. We'll add them all up, right? Add up all little dq's, use the everything's the same, except, what's the difference? The difference is right here. I'm going to add up the charge in each little shell, but when do I stop? I stop when I get to my bubble, because I just care about the charge inside the bubble, inside the Gaussian surface. So I'm going to go from 0 to little r, not to big R. I'm not trying to find all the charge in the sphere, just the charge that's inside the Gaussian surface. So that's the difference. So it'll be the same. Same solution up to a point, up to this line. Okay, same solution until here. When I do that one, my Q in is what I'm trying to find, not the total Q, the Q in, right? Won't be the total, just be some fraction of the total. it'll be an integral from 0 to little r of rho 4 pi r squared dr. Okay, that's the difference right there. We want to stop adding spherical shells when we get to the Gaussian surface. Okay, that's the key, because we just want the Q in our bubble. In this case, the previous problem, all of the sphere was inside our bubble. So we just wanted all of the charge in that charged sphere. Here we want to stop when we get to the bubble. That's it. I think I've said that a million times now. Sorry about that. So that's it. That's the only difference. That's it. And we'll get a different answer out because of that bound is little r instead of big R. And that is it. Should I run through, and that's it. So once I go ahead and I get my Q in, I put it in here, and I go ahead and do my calculation down, move the 4 pi r squared over, and life is good. Right. Remember I said earlier something about the E field being proportional to r to the 4th inside the sphere? That was dumb. That was a mistake. For this one, it's going to be r to the 4th. For the other one, it's not. Now I feel like I need to show you because I said that. You know why? Because when I do this integral, I'm not going to get little r. I'm going to get big R when I put that bound in. And that's not going to cancel with this little r. So outside, it's still proportional to over r squared, of course, right? But for this guy, it's going to be proportional. Inside is proportional to, in this case, r to the 4th. Okay, my bad. Okay, hey, are we okay with this? I hope. So I'm just going to end it there. All right, fine. I've got time. Let me go ahead and work this example for finding the field inside there. I'll work it out the rest of the way, okay? So this is the charge that's inside. I'm going to work it out for this particular case of that density being proportional to 12r cubed. So where it says rho, I'm going to put 12r cubed in there for rho, right? And then when I do my calculation, right, 0 to little r, okay, 4 pi squared little r squared dr. You can say, hey, that 12 and that 4 and that pi, 12, 4 pi are going to pop out. 48 pi integral of r to the 5th dr from 0 to little r. You know what that's going to be? That's going to be 1/6 little r to the 6th, okay, is what I'm going to get out of that integral times 48 pi. That's the Q in. What do I do with that Q in? I put it in here for the charge inside my Gaussian surface in Gauss's law. Again, that left part of the equation is just E times 4 pi r squared. So I'm going to get E times 4 pi r squared is equal to my Q in over epsilon naught. My Q in is going to be, 48 divided by 6? That's 8, right? 6 times 8 is 48. So it'll be 8 pi, right? R to the 6th. Okay? And so what happens now? Move the 4 pi r squared over. If you want that 4 and the pi's cancel out, that's nice, right? That's exciting. 4's and pi's cancel out. I'm just going to end up with 2 r to the 4th over epsilon naught. That's amazing. Okay, cool. Okay, so that's the function that I get. Yeah, 2 r to the 4th over epsilon naught is what that comes out to be. Nice. Nice. Okay, so that's my E field, again, at r less than r, so inside the sphere, proportional to r to the 4th. Outside the sphere, again, going to be proportional to just 1 over r squared. All right. We could do a crazy graph. Want to do a crazy graph? Nah, I don't know. Okay. Well, yeah, we probably should. We probably that. No, I'm just going to cut it off here. Okay. So that's it. So that's what we've been doing here in all these cases in these last 2 videos is looking at charged insulators, insulating spheres. You say, what if it's a conductor? Well, if my sphere is a conductor, right? If I had a metal sphere, and I'm just going to put these last few comments. What if I had a conducting sphere? Well, if the conductor, you remember, because it's a conducting sphere, excess charge is free to move and it will repel each other. And my extra charge always ends up at the surface. Whether it's positive charge or negative charge, the electrons will shift, so the excess charge is at the surface. And so inside, if I did a bubble, it's neutral inside. The extra's at the surface. So inside, you say there's no field lines. If it's a conductor, charges will move. Here's the idea. Inside, they're free to move, and they will move until they balance out that electrical force on them. So the total electric force, when this gets to equilibrium, the total electric force inside a conductor is always zero. So there's no field lines inside. If this guy was charged up, that excess charge would be at the surface, right? There's all my positive charge at the surface for this charged conductor. And you say the E field lines would just radiate outward from the surface, but I would have no field lines inside that sphere. Right? There's no Q, no E inside. Inside here, E is zero. If I do Gaussian surface, there's no charge inside, so that makes sense. Look, if the Q in is zero, this has to also give me zero. It's going to give me zero by having an E of zero. Okay? What happens if I had a spherical shell? What if instead of being a solid metal sphere then, what if it's a hollow metal sphere, a spherical shell? Again, if I charge it up and I put extra charge on it, where's the extra charge going to end up? At the outer surface, not the inner surface, right? Let's just imagine if it was negative, it's easier to picture with the electrons. The electrons would push each other out to the outer edges, right? Inside surface is gonna be neutral, okay? So my excess charge is on the outside, okay? Again, if it was positively charged, the electrons I had would be attracted to the positives and they would stay in and the outer surface would become positive. So the ones that are missing electrons would be at the surface, right? And so again, my charge is at the outside, and my charge is smeared out over that outer surface. In here, again, there'd be no field. It would look just like this picture, right? My field lines would come out from here. In the metal, the field has to be zero. And so inside here, in the metal there, E is zero. And in here, E is zero. Okay? The charge will move in here until electrical force balances out inside and there's no force on the charge inside. Because the conductor, if it was forced, they would move. And so they're going to stop in an arrangement where they have no force on them. So there's no field. If there's no field, then zero, Qn's got to be zero. It's neutral inside. That's it. Which brings me to, sorry, that's not enough for this guy. Interesting question now of what if you now combine these things? What if I have charges nested, charged spheres nested inside other spherical shells, right? And I nest them in each other. What's going to go on then, right? If I had insulating shells, you know that if you're outside the shell, you just treat it like it's a point charge at the center, right? If I'm inside the shell, I just care about the charge that's interior to me. And I have to calculate the amount of charge that's interior to me and then treat that like it's a point charge. Yeah, in fact, well, yeah. I mean, what I'm doing here, if I didn't make that clear, here I found the charge that was interior to me here, in this case. It came out to be, what was this? This came out to be 8 pi r to the 6th, right? Okay, that's the charge interior to me, right? And you say, basically I then treat that like it's a point charge, Q. So I get K times that Q, right, over 1 over 4 pi epsilon naught, right, or squared down. So it's basically treating it like that's a point charge. When I'm outside, if I was outside, which I didn't show you that calculation, sorry about that. If I'm outside, essentially that gets treated like it's a point charge here. Yeah, that's just a charge. Okay, good enough. If I'm inside, what I was saying is the amount that's the fraction of the charge that's interior to me, I treat essentially like it's a point charge if I'm outside. If I'm, you know what I mean? I just care about the charge that's interior. Let's move on. What's interesting though, and we're going to talk about this with problem 3, that's the one that has parts A through L. We'll talk about how to deal with conducting shells and stuff that's nested, okay? And it's easiest to talk through it with an example. And so we'll do that with problem 3 from the homework. And a lot of good stuff will come out of that, and then that will be the end of spherical geometry. Okay, and we'll be able to move on to the last 2 shapes, which are cylindrical, which will go quick, now that you've seen spherical, and planar, which is real fast. All right, and that'll be Gauss's law. All right, hey, that's it. Hope this was useful for you, and I will see you soon.